What if everything we know about the universe is just the surface of something far stranger? Picture standing at the edge of an endless cosmic ocean, staring into depths where the rules of reality twist into shapes we can barely comprehend. The universe isn't just stars and galaxies, it's a labyrinth of hidden structures, invisible dimensions, and mysteries that challenge our very understanding of space and time. And the deeper we look, the more we realize how little we actually know. Think about this for a second. The matter we can see, planets, stars, even our own bodies, makes up less than 5% of the universe. The rest, a shadowy tapestry of dark matter, dark energy, and forces so elusive they might as well be ghosts. Scientists call these the hidden structures of the cosmos, the invisible scaffolding that shapes everything from the birth of galaxies to the fate of the universe itself. But here's the thrilling part: we're just starting to crack the code. Theories are piling up, some wild, some brilliant, all mind-bending, each one a piece of the puzzle waiting to be proven or shattered. This isn't just about equations or distant stargazing. It's about rewriting the story of existence. What if space is threaded with unseen filaments, like cosmic spiderwebs guiding galaxies into place? Could there be extra dimensions curled up so tightly we'll never see them? And if the universe is a hologram, as some physicists suggest, what does that say about the nature of reality itself? Buckle up, because we're about to dive into 30 of the most astonishing theories about these hidden structures, ideas that will stretch your imagination, challenge what you think you know, and maybe, just maybe, leave you seeing the universe in a whole new light. The journey starts now. What if the world around us, every speck of dust, every star in the sky, is nothing more than an illusion, a flickering shadow cast by something far simpler? This is the radical idea behind the holographic universe theory. Imagine watching a movie on a flat screen. The images seem three-dimensional, full of depth and motion, but the truth is, all that complexity is encoded on a flat, two-dimensional surface. Now stretch that idea to the cosmos. Theorists suggest our entire universe might work the same way, a dazzling three-dimensional reality that's actually a projection from information stored on a distant, two-dimensional boundary. The clues come from black holes, those cosmic vacuum cleaners where gravity is so strong not even light escapes. When matter falls into a black hole, it vanishes from our observable universe, but according to the laws of physics, information can never truly be destroyed. So where does it go? Here's the mind bender. The information might be preserved on the black hole's event horizon, the point of no return, encoded like microscopic pixels on a celestial hard drive. This discovery, first hinted at by physicist Jacob Bekenstein and later expanded by Leonard Susskind, suggests a profound link between a black hole's surface and the volume it contains, as if the three-dimensional space inside is somehow written onto its two-dimensional edge. Quantum gravity adds another layer to the puzzle. At the tiniest scales, space itself might be pixelated, made up of indivisible chunks of information. Think of it like a digital photo. Zoom in far enough and you'll see the individual pixels that create the illusion of a smooth image. If the universe is holographic, then what we perceive as empty space could be a tapestry of quantum bits humming with hidden data. The implications are staggering. It would mean the cosmos operates like a cosmic computer, rendering reality in real time, and we're just characters in its simulation. Skeptics argue the theory is still speculative, lacking direct proof. Yet experiments like the holometer at Fermilab have searched for faint ripples in spacetime that could betray this pixelated nature. So far, the results are inconclusive, but the hunt continues. If the holographic principle holds, it wouldn't just rewrite physics, it would force us to confront a dizzying question. Is reality as solid as it seems, or are we all living inside the universe's ultimate projection? Now picture the universe not as a smooth, continuous fabric, but as a cosmic quilt stitched together with bizarre, vibrating threads flaws in space-time itself. These are cosmic strings, theoretical cracks in reality left over from the universe's fiery birth. When the cosmos was just a fraction of a second old, it underwent a dramatic phase transition like water freezing into ice. And just as ice forms cracks as it solidifies, space-time might have developed these infinitesimally thin, unimaginably dense strings, some stretching across the entire observable universe. Gravity bends around these cosmic threads like light warping around a black hole, but with a key difference. While black holes curve space-time into a pit, cosmic strings slice through it like a razor, creating edges so sharp they could distort the path of light passing nearby. This phenomenon, called gravitational lensing, might be our best shot at detecting them. Imagine looking at a distant galaxy and seeing its image mysteriously duplicated as if mirrored, a telltale sign a cosmic string's gravity is splitting the light like a prism. Some astronomers even speculate these strings could have served as gravitational scaffolding in the early universe, guiding matter to clump together and form the first galaxies. Yet for all their potential influence, cosmic strings remain elusive. Some theories suggest they've long since decayed, vibrating themselves into oblivion like snapped guitar strings. Others argue they might still lurk in the voids between galaxies, too faint for current telescopes to spot. The debate hinges on energy scales so extreme they dwarf anything we can recreate in particle colliders. If strings exist, they'd be under unimaginable tension. A single-inch-long segment could weigh as much as Mount Everest. That sheer energy might leave echoes in the cosmic microwave background, the afterglow of the Big Bang, or ripple through space-time as gravitational waves. The hunt continues. Projects like the Laser Interferometer Gravitational Wave Observatory listen for the faint tremors strings might produce, while radio telescopes scan for their lensing fingerprints. Whether relic or myth, cosmic strings force us to confront a profound question. Did the universe leave behind scars as it was born? And if so, could those very scars hold the blueprint for everything we see today? If our universe is just one bubble floating in an endless cosmic foam, how many others are out there, each with its own laws of physics, its own version of reality? This is the staggering premise of the inflationary multiverse, a theory that rewrites the story of creation itself. It all starts with cosmic inflation, that explosive expansion in the universe's first moments when space stretched faster than light. Physicist Alan Guth proposed that this inflation never truly stopped. It just paused in our pocket of the cosmos. Elsewhere, it could still be happening, endlessly birthing new universes like bubbles in a boiling pot. Quantum fluctuations add another twist. Tiny random jumps in energy at the subatomic level might have stretched into colossal ripples during inflation, creating regions where space-time pinched off into entirely separate universes. Some could be nearly identical to ours, with slight tweaks. Maybe gravity is stronger there, or stars burn a different color. Others might be unrecognizable, with dimensions curled in strange shapes or forces we've never seen. And here's the kicker: because inflation stretches space exponentially, these bubble universes would forever drift beyond our cosmic horizon, unreachable even at light speed. Evidence lurks in the cosmic microwave background, the afterglow of the Big Bang. If our universe collided with another bubble long ago, it might have left a faint bruise in that ancient light, a tantalizing clue that astronomers are still searching for. Critics argue the multiverse is untestable by nature, more philosophy than science. But supporters counter that inflation's predictions have already matched observations, from the universe's flat geometry to the pattern of galaxy clusters. If inflation is real, and if quantum chaos can spawn new bubbles, then the multiverse isn't just possible, it might be inevitable. The implications are dizzying. A near-infinite tapestry of realities means every possible version of you could exist somewhere, living out every choice you never made. It also raises haunting questions. If most universes are lifeless with physics too hostile for atoms or light, does that make our existence a statistical fluke? Or is there a deeper principle at work, some unseen hand guiding the cosmos toward life? Whether dream or discovery, the multiverse forces us to confront the wildest idea of all, that everything we know might just be one page in an endless library of realities. String theory paints a picture of reality so vast it makes our universe feel like a single grain of sand on an endless beach. Hidden within its equations are not just one, but perhaps 10 to the 500 possible universes, each with its own unique physics, its own version of existence. This is the multiverse taken to the extreme, a cosmic kaleidoscope where every twist reveals another reality. At the heart of this idea is the concept of the string theory landscape. Imagine a mountain range with countless valleys. Each valley represents a stable configuration of space-time, a place where the laws of physics settle into something coherent. In one valley, gravity might be strong enough to crush atoms instantly. In another, electromagnetism could be too weak to form stars. Our universe just happens to occupy a valley where the numbers line up perfectly for galaxies, planets, and life. This is where the anthropic principle kicks in, a simple but staggering idea that we observe the universe the way it is because if it were any different, we wouldn't be here to observe it. It's like a puddle marveling at how perfectly its hole fits its shape, never realizing the hole could have been any size. Critics argue this reasoning feels circular, even unscientific. But supporters counter that in a multiverse where every possible universe exists, it's no surprise we find ourselves in one that allows us to exist. Testing this theory is where things get thorny. If other universes are forever beyond our cosmic horizon, how could we ever prove they're real? Some theorists look for indirect clues, perhaps collisions between universes left imprints in the cosmic microwave background, like bruises on an apple. Others suggest that the distribution of dark energy or even the mass of the Higgs boson could hint at a broader landscape of possibilities, yet the debate rages on. Is the multiverse a groundbreaking prediction of fundamental physics or just an untestable leap of imagination? The answer might lie in the fabric of reality itself, woven not just with strings but with questions we're only beginning to ask. What if every choice you've ever made, every crossroads, every hesitation split the universe into two? Welcome to the many worlds interpretation, where reality isn't a single path but an endlessly branching tree, sprouting new timelines with every quantum flicker. Forget parallel universes floating in some distant void. These alternate realities are stacked right on top of ours, separated by the thinnest veil of probability. Start with Schrödinger's cat, that famous thought experiment where a feline in a box is both alive and dead until someone peeks inside. In the classic view, observation collapses the cat into one state. But Many Worlds flips the script. The cat doesn't choose, it splits. In one reality, it purrs happily. In another, it's gone. Both outcomes happen, just in different branches of existence. Every quantum event, a particle spinning left or right, an atom decaying or not, becomes a fork in the road, with the universe duplicating itself to accommodate every possible outcome. The implications are staggering. Missed a bus somewhere, you caught it. Lost a bet, another you is celebrating. While it sounds like science fiction, the math checks out. Physicist Hugh Everett proposed this in the 1950s to dodge the weirdness of quantum collapse. No mysterious observer effect, no privileged moment when reality picks an outcome, just endless divergence, like a hall of mirrors reflecting every path not taken. Critics pounce on one glaring issue. If these branches are forever out of reach, how do we test them? Proponents argue the theory isn't about observation but consistency. The equations hold without adding extra rules. Some suggest quantum computers could leave fingerprints of branching, or that rare quantum effects might let branches briefly brush against each other. Others counter that untestability makes it metaphysics, not science. yet the idea lingers because it solves puzzles. Why does quantum math work so flawlessly if reality isn't truly branching? Could consciousness itself be a tapestry woven across countless versions of you? Whether prophecy or pipe dream, many worlds forces us to ask, are we the authors of our fate or just one thread in a vast, unraveling story? Galaxies aren't just drifting aimlessly through the cosmos, some are being pulled, as if by an unseen hand, towards something we can't see, something beyond the edges of our observable universe. Scientists call this eerie phenomenon dark flow, and it's one of the most baffling mysteries in modern astronomy. Picture throwing a handful of leaves into a river. Most move with the current, but a few cling to an invisible undertow, dragged in a different direction. That's what's happening to entire galaxy clusters, thousands of them, all streaming toward a single point in space like cosmic iron filings drawn to a magnet. The first clues surfaced in 2008, when astronomers studying the cosmic microwave background, the faint glow left over from the Big Bang, noticed something strange. The light from distant galaxy clusters showed subtle distortions, as if they were moving much faster than expected, all in the same direction. These weren't random motions. They pointed toward a patch of sky near the constellations Centaurus and Vela, suggesting a gravitational pull from something outside our observable universe. The scale is staggering. These clusters are racing at hundreds of kilometers per second across distances of billions of light years, defying the uniform expansion we expect from dark energy. So what's tugging them? One radical possibility is that our universe isn't alone. Just as Earth's gravity affects the Moon, a neighboring universe, or something even stranger, might be exerting its pull from beyond the cosmic horizon. Imagine two soap bubbles floating close together. The gravity from one could dent the other, creating a directional tug we perceive as dark flow. Other theorists propose it's a remnant of the violent pre-inflation era, a cosmic scar from when space-time was stretched unevenly during the Big Bang. Skeptics argue it could be a measurement error or a local effect from unseen superclusters, but the data persists, and newer surveys like the Planck satellite have only deepened the mystery. If dark flow is real, it shatters the assumption that the universe is uniform on the largest scales, and hints that there's far more out there than we'll ever see. The unsettling truth: we might be living in a cosmic backwater, caught in the wake of something unimaginably vast. What if the Big Bang wasn't a beginning but just another chapter in an endless cycle of cosmic rebirth? Enter the Big Bounce, a theory that rewrites the universe's origin story, not as a single explosive moment, but as the latest bounce in an eternal rhythm of expansion and contraction. Imagine the cosmos as a colossal lung, breathing in and out over trillions of years, collapsing inward only to spring outward again in a new fiery genesis. The standard Big Bang picture runs into trouble when we rewind time all the way back to the singularity, a point of infinite density where the laws of physics break down. But quantum gravity, a still emerging theory aiming to unite Einstein's relativity with quantum mechanics, suggests nature might abhor infinities after all. At the tiniest scales, spacetime could be granular, like the pixels on a screen, preventing total collapse. Instead of a singularity, the universe might reach a maximum density and then rebound. Picture squeezing a rubber ball with all your strength. Just as it can't shrink further, it snaps back. Cyclic cosmology takes this further, proposing that each big crunch births a new expansion with slightly different physics. Black holes from the previous cycle might seed new galaxies. Dark energy's push and pull could set the tempo. The appeal, no messy beginning, to explain just an endless cosmic heartbeat. Some versions even suggest these cycles could explain why our universe's constants seem finely tuned for life. With each bounce, the numbers shuffle, and we happen to live in a cycle where the deck was dealt just right. Evidence is scarce but tantalizing. If a prior universe left imprints in the cosmic microwave background like echoes of a drumbeat, future telescopes might spot them. Others look for signs of phantom dark energy, a force that could one day reverse expansion. Skeptics argue that without observable cycles, the theory remains poetic speculation. Yet it forces us to confront a profound question. Is time itself circular, with every ending just a prelude to another beginning? The stakes couldn't be higher. If the Big Bounce is real, our universe isn't a one-time wonder. It's a phoenix forever rising from its own ashes, and that changes everything. What if our universe wasn't born from a fiery explosion, but from a silent collision between two ghostly parallel worlds? This is the daring premise of the ekpyrotic universe theory, a cosmic origin story ripped straight from the pages of string theory. Picture two infinite sheets floating in higher dimensional space, membranes stretched thinner than atoms yet vast enough to contain entire realities. These aren't just abstract ideas, they're called branes, short for membranes, and according to this model, our universe began when two of them smashed together like cymbals in the dark. The ekpyrotic scenario turns the Big Bang on its head. Instead of a singularity exploding from nothing, it imagines a universe reborn from wreckage. Energy from the collision would have flooded our brain, heating it to unimaginable temperatures and seeding the matter we see today. Remarkably, this could explain why the cosmos appears so uniform, those distant corners of space glowing with identical temperatures. In the classic Big Bang, scientists invoke inflation to stretch space smooth, but here, the branes themselves act like rolling pins, flattening irregularities across eons before the crash. String theory's extra dimensions give this idea weight. We experience only 3 dimensions of space, but if others exist curled up impossibly tiny, then branes could drift through them unseen. The collision wouldn't be a one-time event either. Cyclic brane models suggest these crashes happen over and over, with universes expanding, cooling, and then drawn back for another collision by hidden forces, like a cosmic pendulum swinging through higher dimensions. But how could we ever test such a wild idea? The smoking gun might lie in gravitational waves. A brane collision wouldn't be gentle, it would send tremors through space-time itself. Future detectors could hunt for a specific pattern in these ripples, a fingerprint of branes clashing rather than black holes merging. Another clue could lurk in the cosmic microwave background. While inflation predicts near-perfect uniformity, ekpyrosis might leave subtle swirls in the polarization of ancient light, a signature of those pre-crash wrinkles. Critics argue the theory relies too heavily on unproven string theory mathematics, and without direct evidence it remains speculative. But its elegance is undeniable, a universe born not from chaos, but from the slow, inevitable dance of dimensions we can't even see. Whether fact or fable, the ekpyrotic model forces us to ask, could our entire existence be the echo of a collision in the dark? What if everything you've ever felt, seen, or experienced, every star, every heartbeat, even the sting of a paper cut, was just lines of code in an unfathomably advanced simulation? This isn't sci-fi, it's the simulation hypothesis, a theory that's gained startling traction among scientists and philosophers alike. At its core is a simple but chilling idea. If civilizations inevitably reach the technological capacity to create hyper-realistic simulations of their ancestors, and if they have any desire to do so, then the odds are overwhelming that we're living in one of those simulations rather than the original reality. Philosopher Nick Bostrom laid out this argument with mathematical precision in what's now called the Bostrom trilemma. He proposed 3 possibilities, at least one of which must be true. First, almost no civilization reaches the technological stage to run ancestor simulations, perhaps because they self-destruct first. Second, even if they could, they choose not to. Or third, we're almost certainly living in a simulation right now. The logic is merciless. If even a tiny fraction of civilizations run simulations, the number of simulated minds would dwarf biological ones, making it statistically improbable we're among the real originals. The Fermi paradox, the eerie silence of the cosmos despite its vast age, might even find an explanation here. If civilizations inevitably create simulations, they might retreat inward, abandoning interstellar exploration for digital utopias. Or worse, the universe seems empty because it's a pared-down simulation, its creators optimizing processing power by not rendering alien life. Even quantum indeterminacy, where particles exist in blurred states until observed, could be a telltale sign of computational shortcuts, like a video game only rendering graphics when the player looks. But critics pounce on a glaring flaw. If the simulation is perfect, how could we ever prove it's there? Falsifiability, the bedrock of science, seems impossible when any evidence could itself be part of the program. Some suggest hunting for glitches, like anomalies in high-energy physics experiments where the simulation might cut corners. Others argue the hypothesis is metaphysics masquerading as science, a modern-day version of, are we living in a God's dream? Yet the idea lingers because it reframes existential questions in terrifying new ways. If we're simulations, do our choices matter? Could the simulators intervene? And if we one day create our own simulations, would that make us gods, prisoners, or something else entirely? Whether prophecy or paranoia, the simulation hypothesis forces us to confront the unnerving possibility that reality might be thinner than we think, and the truth could be lurking just beyond the rendered distance. Black holes aren't just cosmic vacuum cleaners, they might be cosmic wombs, birthing entire universes from their crushing depths. This is the mind-bending premise of the black hole universe theory, which flips the script on everything we thought we knew about reality. Picture a black hole in some distant, unimaginably vast parent universe, its event horizon stretching like an infinite curtain. Beyond that point of no return, space and time twist so violently that the rules of physics as we know them shatter. But what if in that chaos an entirely new universe is taking shape? Think about how black holes behave. At their core lies a singularity, a point of infinite density where matter is crushed beyond recognition. But here's the puzzle. Singularities don't play nice with quantum mechanics, which abhors infinities. Loop quantum gravity, a leading contender for unifying relativity and quantum theory, suggests singularities might not be infinitely dense after all. Instead, they could reach a maximum compression, a cosmic bounce point where gravity's crush rebounds into an explosive expansion. Sound familiar? It's eerily reminiscent of the Big Bang, leading some theorists to propose that our universe might have ignited from such a bounce inside a black hole's heart. Hawking radiation adds another layer of intrigue. Black holes aren't entirely black, they slowly leak energy, evaporating over eons. But if our universe is nestled inside one, that evaporation could explain dark energy, the mysterious force accelerating cosmic expansion. Imagine the black hole's energy loss leaking into our space, pushing galaxies apart like an invisible tide. Even the uniformity of the cosmos fits. Matter falling into a black hole gets stretched and homogenized at the event horizon, mirroring the smoothness we see in the cosmic microwave background. Of course, skeptics raise valid questions. If universes spawn inside black holes, where did the parent universe come from? Its turtles all the way down, an infinite regression of cosmic nesting dolls. Testing the theory is another hurdle. We can't peek beyond our own universe's event horizon, and any signals from the outside would be scrambled beyond recognition. Yet the math holds a strange allure, suggesting an elegant symmetry. Just as black holes trap light, they might also trap entire realities, each with its own laws, its own story. Whether fact or cosmic poetry, the black hole universe theory forces us to rethink our place in the grand scheme. Are we the result of a celestial collapse, a cosmic phoenix rising from the ashes of another universe's death? If so, then every star, every planet, every atom might just be the echoes of a singularity's last gasp written into something new. Ever looked at a snowflake under a microscope and marveled at how the same intricate pattern repeats itself no matter how much you zoom in? Now imagine that same principle governing the entire cosmos, a universe where galaxies, stars, and even the voids between them arrange themselves in endlessly repeating, self-similar patterns. This is the radical vision of the fractal universe theory, a challenge to one of astronomy's most sacred assumptions, that on the largest scales, the universe is smooth and uniform. The Standard Model relies on the cosmological principle, the idea that if you step back far enough, matter distributes itself evenly. No special places, no grand designs, just a cosmic soup of homogeneity. But dig into the data and something curious emerges. Galaxy surveys show clusters clumping into filaments and walls, forming a cosmic web that looks suspiciously like the branching veins of a leaf or the lightning bolt's jagged path. These structures appear to echo across scales, from the local supercluster to the faintest wisps of matter at the edge of observation. Mathematician Benoit Mandelbrot, who coined the term fractal, argued that the universe might not play by the rules of smoothness at all. Instead, it could be a fractal, infinitely complex no matter how closely you examine it. Detractors point to the cosmic microwave background, the afterglow of the Big Bang, which shows near-perfect uniformity in every direction. If the universe were truly fractal, they argue, that primordial light should bear the scars of unevenness. Yet proponents counter that even in a fractal cosmos there's a cutoff, a scale where smoothness emerges not from uniformity, but from the sheer density of repetition. Think of a mountain range. Up close, it's jagged and chaotic, but from space it blends into Earth's curve. The debate hinges on whether we're seeing the forest or just getting lost in the trees. Newer galaxy catalogs add fuel to the fire. Projects like the Sloan Digital Sky Survey reveal structures so vast they defy conventional scaling, like the Hercules Corona Borealis Great Wall, a filament of galaxies stretching 10 billion light-years, a potential fingerprint of fractal geometry. If confirmed, it would mean rewriting textbooks. Instead of a universe governed by simplicity at scale, we'd inhabit a cosmos of endless complexity, a Russian nesting doll where every layer reveals new wonder. The implications stretch beyond astronomy. A fractal universe suggests nature operates by universal rules, linking the quantum to the cosmic. It's the difference between seeing reality as a blank canvas or an infinite tapestry, one where every thread, no matter how small, is part of a grander pattern we're only beginning to trace. Time crystals sound like something ripped straight from a sci-fi novel, structures that don't just exist in space but loop endlessly through time itself. Unlike diamonds or snowflakes with their repeating patterns in 3 dimensions, time crystals are locked in an eternal dance, cycling through states over and over without ever losing energy. The idea was so radical that when Nobel Prize-winning physicist Frank Wilczek first proposed it in 2012, many dismissed it as impossible. After all, how could something move perpetually without breaking the sacred laws of thermodynamics? Yet today, these exotic structures don't just exist in theory, they've been cooked up in labs, defying expectations and forcing us to rethink the very fabric of reality. Wilczek's insight was deceptively simple. What if matter could form patterns not just in space but in time? Picture a pendulum swinging forever without friction, or a clock ticking infinitely without winding. Normally, such perpetual motion is forbidden. Energy dissipates, systems settle into equilibrium. But time crystals exploit a loophole. They're not perpetual motion machines. Instead, they're systems that settle into a stable, repeating rhythm when nudged by an external force, like a drum that keeps beating long after the drummer stops. In 2017, researchers at the University of Maryland and Harvard made the first experimental versions using chains of ytterbium atoms, while others created them with diamond defects or even quantum computers. The key signature: these systems tick at a frequency unrelated to the force driving them, like a metronome set to its own mysterious tempo. Now imagine scaling this up to the cosmos. If time crystals can exist on a quantum scale, could space-time itself harbor similar structures, hidden rhythms woven into the universe's foundation? Some theorists speculate that dark matter, that elusive cosmic glue, might consist of time crystalline phases, its particles oscillating in sync across billions of years. Others suggest the Big Bang's aftermath could have left temporal defects in space-time, wrinkles where causality itself stutters. Even black holes might play a role, their event horizons acting as time mirrors that trap these strange oscillations in gravitational limbo. The implications are staggering. Time crystals challenge our most basic assumptions about equilibrium, suggesting that certain systems never truly settle. They just find new ways to dance. If space-time itself has crystalline properties, it could mean the universe isn't just a static stage but a dynamic, pulsating entity, with hidden gears turning beneath the surface of reality. Whether cosmic curiosity or fundamental truth, one thing's certain: time crystals have cracked open a door to a world where time isn't just a dimension, it's a material waiting to be sculpted. Somewhere in the vast emptiness between galaxies, an invisible force is working tirelessly, not just pushing the universe apart, but stretching the very fabric of reality like hot taffy. This is phantom energy, dark energy's most extreme and terrifying incarnation. While ordinary dark energy accelerates cosmic expansion gently, phantom energy grows stronger over time, its power compounding until space itself can't withstand the tension. The result: a doomsday scenario known as the Big Rip, an apocalypse so absolute it wouldn't just destroy galaxies or stars, but dismantle atoms, space-time, and perhaps even the fundamental laws of physics. The nightmare begins with the Hubble constant, the rate at which the universe expands. Today, galaxies drift apart slowly, their gravity fighting dark energy's push. But phantom energy doesn't play by those rules. Imagine blowing up a balloon where the rubber gets thinner the more it stretches, weakening until it can't hold together. Similarly, as phantom energy intensifies, it would first tear galaxy clusters apart, then individual galaxies. Stars would be plucked from their orbits, planets ripped from their suns. Next comes the gruesome part. As expansion accelerates beyond all limits, gravity and even nuclear forces would lose their grip. Hours before the end, Earth would explode as phantom energy overcomes the bonds holding its atoms together. In the final milliseconds, molecules, then atoms themselves, would be shredded into quantum confetti. Even space-time, the stage on which reality plays out, might fracture like thin ice, leaving behind a void so profound that not even mathematics could describe it. What makes this scenario so unsettling isn't just the violence of the end, but the inevitability. If phantom energy exists, its effects are already baked into the cosmos, ticking away like a doomsday clock set to approximately 22 billion years. The James Webb Space Telescope might hold clues. By measuring how dark energy's strength changes over time, astronomers are hunting for hints that it's evolving into something far worse. So far, data suggests dark energy is constant, but the margin for error leaves room for horrors. Yet here's the twist: phantom energy might not spell oblivion but transformation. Some theories suggest a Big Rip could tear open portals to other dimensions or trigger a new Big Bang in the carcass of our universe. After all, nature abhors a vacuum, and in the smoking ruins of space-time, who's to say what strange new physics might emerge? Whether finale or rebirth, one thing's certain: if phantom energy is real, the universe's fate won't just be cold and dark, it'll be loud, messy, and over in the blink of a cosmic eye. The cosmic microwave background should be the ultimate equalizer, a near-perfect snapshot of the infant universe, glowing with the same temperature in every direction. But when scientists mapped it with unprecedented precision, they stumbled upon something that shouldn't be there: a strange, invisible line slicing through the cosmos like a scar, a ghostly axis where temperatures subtly align in a way that defies randomness. Dubbed the axis of evil by researchers half-jokingly, this anomaly doesn't just raise eyebrows, it threatens to upend one of cosmology's most sacred principles, that the universe has no preferred direction, no up or down on the grandest scales. First spotted by NASA, a Wilkinson microwave anisotropy probe in the early 2000s, the axis of evil refers to an eerie correlation in the CMB's fluctuations along a particular plane of the sky. Imagine rolling a die thousands of times and always getting slightly more sixes when the die faces north. That's the level of statistical unease this pattern creates. Some regions of the CMB appear warmer, others cooler, but these variations aren't scattered randomly. Instead, they loosely align along this axis, as if the universe itself tilted during its birth, leaving a faint thumbprint on everything that followed. Critics argue it's just noise, a fluke of measurement, or an artifact of our solar system's motion through space. After all, the CMB's temperature variations are minuscule, differing by less than 1/1000th of a degree. But the Planck satellite, the most advanced CMB mapper to date, later confirmed the anomaly, deepening the mystery. If not an error, the implications are staggering. It could mean the universe isn't isotropic as we've assumed. Perhaps it's lopsided on scales so vast we've never noticed. Some theorists even speculate it's a relic of pre-Big Bang physics, a cosmic bruise left by a collision with another universe during inflation. The controversy cuts to the heart of how science confronts the unexpected. Do we dismiss outliers as noise, or do they hint at deeper truths? For now, the axis of evil remains an open case, a tantalizing "what if" scribbled in the margins of cosmology's textbooks. Whether it's a clerical error in the cosmos or a clue to a grander reality, one thing's certain: the universe loves to keep us guessing. Here's a mind-bending thought. What if your consciousness, your memories, even this very moment you're experiencing right now, didn't evolve in an orderly universe over billions of years, but simply popped into existence randomly, fully formed from the chaotic churn of quantum fluctuations? This is the unsettling premise of the Boltzmann brain paradox, a thought experiment that turns our understanding of reality inside out. The puzzle starts with entropy, the universe's tendency toward disorder. In the 19th century, physicist Ludwig Boltzmann proposed that while entropy generally increases, tiny pockets of order can spontaneously arise purely by chance, like finding a perfectly stacked deck of cards in a tornado's wreckage. Fast forward to the modern multiverse, where infinite time and space amplify these odds. Statistically, it becomes far more likely for a single, self-aware brain to materialize randomly, complete with fake memories of a past that never happened, than for an entire ordered universe like ours to emerge. After all, one brain requires far less improbable order than galaxies, planets, and evolution. The implications are dizzying. If Boltzmann brains dominate the multiverse, how do we know we're not one of them? Every time you recall a childhood memory or observe the cosmic microwave background's uniformity, it could just be an elaborate illusion conjured by quantum chaos. Some interpretations of quantum mechanics even suggest consciousness plays a role in collapsing probabilities into reality, adding eerie fuel to the fire. Critics counter that the paradox relies on extreme extrapolations of statistical mechanics. Maybe universes with stable physical laws are more probable than fleeting brains, or perhaps consciousness can't exist without a material framework. Others invoke the anthropic principle. Boltzmann brains would dissolve instantly, leaving only real observers like us to ponder the question. But the theory's persistence highlights a deeper unease. In an infinite cosmos governed by probability, can we ever truly trust our perception of reality? What makes the Boltzmann brain so haunting isn't just the science, it's the philosophical vertigo. If existence is a game of chance, then truth and illusion blur into one. The universe might not just be stranger than we imagine, It might be stranger than we can imagine, a hall of mirrors where even the mirrors aren't real. Black holes devour everything in their path, but what if there exists a cosmic mirror image, an object that only spews matter out, refusing to let anything in? Meet the white hole, black hole's theoretical twin, a place where the rules of gravity run backward. While black holes trap light, white holes repel it. Where black holes crunch matter into oblivion, white holes spit it out with unrelenting force. The equations of general relativity don't just allow for these strange objects, they demand their existence as natural counterparts to the darkness we've come to know. Einstein's field equations are symmetric, meaning mathematically, what goes in must eventually come out. Picture a river flowing into a black hole's waterfall. A white hole would be that same waterfall in reverse water, bursting upward with such intensity that nothing can push its way down. Some theorists speculate the Big Bang itself could have been a white hole event, a violent eruption of space-time birthing our universe from the collapse of another. Others suggest white holes might be the other end of black holes, connected by wormholes in a cosmic plumbing system where matter vanishes in one place only to reappear somewhere else or someone else. Quantum gravity complicates the picture. While general relativity suggests white holes could form, quantum mechanics insists that entropy, the universe's tendency toward disorder, must always increase. A white hole defies this, appearing to unscramble matter and energy in a way that seems to reverse time's arrow. But here's the twist: loop quantum gravity, a leading theory attempting to unite relativity and quantum mechanics, predicts that black holes could eventually rebound into white holes after evaporating via Hawking radiation. Instead of disappearing into a singularity's oblivion, a dying black hole might transform, its core bouncing back like a compressed spring, ejecting all it once consumed. The challenge: observational evidence is non-existent. White holes would shine blindingly bright, spewing radiation at energies dwarfing quasars, yet we've never spotted one. Some argue they're inherently unstable, collapsing instantly into black holes the moment they form. Others propose they exist only in the universe's distant future or its distant past. But if they're real, they could rewrite cosmic history, offering a bridge between singularities and the smooth expanse of space we see today. Perhaps the most tantalizing idea is that white holes aren't just relics of math, but active players in the cosmos. Could dark matter's mysterious pull be the gravitational shadow of white holes lurking unseen? Might gamma-ray bursts, the universe's most violent explosions, be their death throes? Until we find proof, they remain a ghost in the equations, a reminder that the universe's strangest secrets might not lie in the voids we observe, but in the echoes of what they've left behind. What if our universe has a hidden twin, a mirror image where time flows backward and matter is replaced by its antimatter counterpart? This isn't just science fiction. It's a serious prediction rooted in one of physics' most fundamental symmetries, CPT, short for charge, parity, and time. The idea is as elegant as it is bizarre. Flip a particle's charge, mirror its spatial coordinates, and reverse the arrow of time, and the laws of physics should hold perfectly. But here's the kicker. If you apply all three transformations at once, the math suggests you'd create a universe that's mathematically identical to ours, yet running in reverse, like a cosmic film played backward. Take antimatter, for instance. Every electron has its antimatter twin, the positron, identical in mass but with opposite charge. Now imagine entire galaxies made of these antiparticles, stars burning with antimatter fuel, even anti-you reading an anti-script. CPT symmetry insists this mirror cosmos isn't just possible, it might be inevitable. Some theorists argue that the Big Bang didn't just produce our universe but spawned two, one dominated by matter, the other by antimatter, each moving in opposite directions through time. Known as the anti-universe, this shadow realm would be forever out of reach, its light unable to cross the temporal divide. Yet its existence could solve one of cosmology's greatest puzzles. why our universe has so much matter and so little antimatter. But the implications go deeper. Neutrinos, those ghostly particles that barely interact with matter, might hold the key. Unlike other particles, neutrinos seem to violate parity symmetry. They spin only counterclockwise, never clockwise, as if they're sensitive to some cosmic handedness. If the anti-universe exists, it could explain this asymmetry, with neutrinos acting as messengers between the two realms. Even dark matter, that invisible scaffolding holding galaxies together, might find an explanation here. The mirror universe's particles could be bleeding gravitational influence into our spacetime, tugging on stars and galaxies without ever directly interacting with light. Of course, skeptics abound. How do you test a universe you can't observe? Some propose hunting for subtle imbalances in cosmic rays or neutrino oscillations that betray the anti-universe's influence. Others look for anomalies in the cosmic microwave background, perhaps a faint temperature gradient pointing toward the mirror realm's gravitational pull. The challenge is monumental, but the payoff would rewrite reality itself. Whether fact or fantasy, the mirror universe forces us to confront a profound truth. Symmetry might be the universe's deepest language, and we're only just learning to speak it. What if gravity isn't a fundamental force at all, but something far stranger, a side effect of the universe's relentless slide into chaos? This is the radical proposition of entropic gravity, a theory that turns 3 centuries of physics on its head. Dutch physicist Erik Verland threw down the gauntlet in 2010 with a startling claim. Gravity doesn't exist as an independent force. Instead, it's an illusion, a thermodynamic mirage emerging from the way information gets shuffled in the fabric of spacetime. Think of the universe as a cosmic hard drive where every particle stores bits of data. When matter moves, it alters the surrounding information landscape, much like a stone rippling the surface of a pond. But here's the twist. Entropy, the measure of disorder, dictates how this information reorganizes. Verland's math suggests that what we perceive as gravity is actually spacetime's way of maximizing entropy, like a cosmic game of Tetris where matter naturally slides toward configurations that create the most chaos. Suddenly, Newton's apple doesn't fall because of some invisible pull. It's following the path of least resistance in an entropic cascade. This isn't just poetic imagery. Entropic gravity recasts Einstein's general relativity as a holographic effect. Just as heat emerges from the random motion of atoms, gravity might emerge from microscopic degrees of freedom we can't yet see. The theory even predicts subtle deviations from Einstein's equations in extremely weak gravitational fields, precisely where dark matter's effects are most puzzling. Some researchers argue this could explain galactic rotation curves without invoking invisible particles. Instead of dark matter's gravitational tug, galaxies behave as if they're caught in an entropic gradient, their stars pushed outward by the universe's hidden information flow. Skeptics counter that Verland's framework lacks the precision of quantum field theory, and experiments like the Laser Interferometer Gravitational Wave Observatory haven't detected any anomalies that favor entropic gravity over general relativity. Yet the theory's allure lies in its unifying power. If gravity is entropy in disguise, it bridges thermodynamics, information theory, and quantum mechanics, a trifecta physicists have chased for decades. The debate crystallizes around one haunting question. Are we mistaking the universe's bookkeeping for its laws? Whether entropic gravity reshapes physics or fades as a beautiful mirage, it forces us to reconsider the bedrock of reality. After all, if something as fundamental as gravity can be emergent, what else might be hiding in the fine print of cosmic chaos? Deep inside every black hole, beyond the crushing grip of the event horizon, there might not be a singularity waiting, but a star. Not the blazing, gaseous giants we know, but something far stranger, a Planck star, a remnant of the original collapsed object squeezed to the absolute limits of density allowed by quantum physics. This idea shatters the classical picture of black holes as bottomless pits, suggesting instead that they harbor ultra-dense cores, cosmic time capsules waiting to detonate. At the heart of this theory lies quantum gravity's defiance of the infinite. General relativity predicts that matter falling into a black hole gets crushed into an infinitely dense point, a singularity where space-time curvature becomes meaningless. But nature abhors infinities, and quantum mechanics insists there's a smallest possible scale, the Planck length, about 10 to the power of -35 meters. A Planck star is what happens when a collapsing star reaches that threshold, a fiery orb smaller than an atom yet containing the mass of a sun. Its density so extreme that not even gravity can compress it further. Like a spring pressed to its limit, it rebounds in a violent explosion. But here's the twist: because time slows to a crawl near a black hole's event horizon, that detonation could take billions of years from our perspective, meaning the universe's first black holes might be ticking time bombs set to go off any eon now. How would we spot such an event? Gamma-ray bursts, the most energetic explosion since the Big Bang, could be the smoking guns. When a Planck star finally rebounds, it would unleash a torrent of radiation as it punches through the black hole's outer layers, creating a burst so bright it could outshine entire galaxies. Astronomers have already catalogued thousands of these mysterious flashes, some with energy profiles that don't quite fit supernova models. Could a handful be Planck stars announcing their resurrection? The timing fits. If the earliest black holes formed around 13 billion years ago, their delayed explosions would be lighting up the cosmos right about now. But the implications go far beyond fireworks. Planck stars could solve the black hole information paradox, the puzzle of what happens to the data encoded in matter that falls inside. If black holes eventually explode, that information isn't lost forever. It's merely locked away until the star's rebirth. Loop quantum gravity, a leading framework for uniting quantum mechanics and relativity, naturally predicts these rebound effects, offering an elegant escape from the paradox's grip. Even Hawking radiation, the slow leak that causes black holes to evaporate, might get a reinterpretation not as a whisper of dying space-time, but as the first tremors of a Planck star's impending eruption. Of course, not everyone's convinced. Critics argue that without direct evidence linking gamma-ray bursts to primordial black holes, Planck stars remain speculative. Others question whether quantum gravity's effects would be strong enough to halt collapse completely. Yet as telescopes grow sharper and gravitational wave detectors more sensitive, we might soon catch a telltale flash, a cosmic phoenix rising from its own ashes, rewriting the lifespan of black holes in a single blinding instant. Until then, the universe keeps its secrets close, reminding us that even the darkest voids might be hiding the brightest fires. Picture the universe not as a scattered sea of galaxies, but as a colossal spiderweb, its strands woven from something utterly invisible. These aren't ordinary threads, they're rivers of dark matter, flowing through the cosmos in vast, intricate filaments, stretching billions of light years to connect galaxy clusters like beads on a string. This is the cosmic web's hidden skeleton, a scaffolding so delicate yet so powerful it dictates where galaxies form, how they move, and even how they collide. The most stunning part, we can't see it directly. Dark matter doesn't emit, absorb, or reflect light. It only whispers its presence through gravity. But thanks to supercomputer simulations like Illustris and Eagle, we've begun to trace its ghostly contours. These programs crunch unimaginable amounts of data, simulating billions of years of cosmic evolution to reveal how dark matter's tendrils snake through the void. The results are mesmerizing. Luminous galaxies huddle along these filaments like cities along highways, while the voids between them stretch empty, devoid of dark matter's pull. It's as if the universe is a grand neural network, with dark matter as the axons carrying invisible signals. Mapping these structures in the real world is a Herculean task, but astronomers have tricks up their sleeves. One method involves gravitational lensing, the way dark matter's gravity bends light from distant galaxies, warping their shapes like a funhouse mirror. By studying these distortions, scientists can reconstruct the hidden mass. Another clue comes from the cosmic microwave background, where dark matter's gravitational fingerprints leave faint temperature variations. Projects like the Dark Energy Survey and the upcoming Euclid spacecraft are stitching together these clues, slowly revealing the web's architecture. The implications are staggering. These filaments aren't just passive backdrops, they're dynamic highways guiding galaxies into collisions and mergers. When clusters smash together, like the famous bullet cluster, the dark matter strands pass through unscathed, leaving visible matter trailing behind like debris in a cosmic wake. Some theorists even suggest dark matter filaments could harbor exotic particles or primordial black holes, relics from the universe's first moments, yet mysteries linger. Why do some filaments appear denser than others? Could they funnel dark matter into galaxies, fueling their growth? And if we ever mapped the entire web, would it reveal patterns pointing to deeper laws? For now, the filaments remain shadowy sketches on the edge of perception, but with every new simulation, every lensing survey, we're pulling back the veil on the universe's darkest secret. Beneath the cosmic ballet of stars and galaxies, an ocean of ghostly particles flows unnoticed, trillions of neutrinos streaming through your body every second, as indifferent to matter as wind to a mountain. These cosmic phantoms, born in the hearts of stars and the fury of supernova, might hold one of the universe's greatest secrets. What if their collective whisper is nudging the cosmos apart? Neutrinos are the ultimate escape artists. They barely interact with matter, passing through planets like sunlight through glass. For decades, physicists assumed they were massless until experiments like Super Kamiok and caught them oscillating, changing flavors between electron, muon, and tau types mid-flight. This chameleon act proved they must have mass, however tiny. But here's the catch: we still don't know how much. The mass hierarchy problem divides theorists into two camps: those who believe neutrinos are lightweight even by subatomic standards, and those who argue some might be hefty enough to reshape the cosmos. Now imagine all those neutrinos, relics from the Big Bang and later stellar explosions, filling space like an invisible gas. Their combined gravitational pull could be tweaking the universe's expansion, acting as a secondary dark energy. Some models suggest cosmic acceleration isn't just dark energy's doing, but a tag-team effort with neutrinos subtly amplifying the effect. The math gets wilder. If neutrinos have a so-called secret interaction, where they interact with each other via an unknown force, their sea could clump into dense pockets, mimicking dark matter's gravitational scaffolding. The hunt for answers is on. Experiments like IceCube in Antarctica and the upcoming Deep Underground Neutrino Experiment are racing to pin down neutrino masses and behaviors. If they find even slight deviations from predictions, it could rewrite our understanding of cosmic expansion. Picture a universe where the smallest particles hold the largest levers, where ghosts from the Big Bang are quietly steering galaxies apart. Critics argue neutrinos are too lightweight to matter on cosmic scales, but supporters counter that small effects add up over billions of years. After all, the universe is patient, and even the faintest tug can bend the arc of eternity. Whether key players or cosmic background noise, neutrinos remind us that sometimes the most profound truths hide in the lightest touch. What if the laws of physics as we know them aren't permanent, but temporary, a fragile arrangement waiting to collapse like a house of cards? This is the spine-chilling premise of vacuum decay, a catastrophe scenario where the universe's fundamental rules could rewrite themselves in an instant, erasing everything we know faster than a blink of light. At the heart of this existential threat lies the Higgs field, the invisible energy blanket that gives particles their mass. We've long assumed it's stable, like a ball resting at the bottom of a valley. But what if that valley isn't the lowest point? What if there's a deeper pit, a true vacuum state, lurking just beyond the horizon of our current physics? The math is as unsettling as it gets. Quantum fluctuations could theoretically punch a microscopic bubble of this true vacuum into existence anywhere, anytime. Once formed, it would expand at light speed, its walls rewriting the very fabric of reality as they go. Atoms would disintegrate, forces like electromagnetism and gravity might vanish or morph into something unrecognizable, and the universe as we know it would cease mid-thought. Stephen Hawking famously ranked this among the universe's greatest dangers, a silent apocalypse with no warning. One moment you're sipping coffee, the next your coffee and the molecules composing it no longer obey the rules that let them exist. Here's the twist: we might already be living on borrowed time. The Higgs boson's mass measured at CERN suggests our vacuum is metastable, not perfectly stable but balanced on a knife's edge. Think of it like a marble perched on a mountain ridge. Given enough time, quantum jitters could nudge it into the abyss. The good news: estimates put the average waiting time at billions of years. The bad news: quantum events don't follow schedules. A decay bubble could form tomorrow or never, but once it does, physics offers no escape. Not even light outruns the rewriting of spacetime itself. Could we detect the approach of such a bubble? Unlikely. Its boundary would arrive without precursor, a wall of new physics moving too fast to signal its coming. Some theorists speculate advanced civilizations might attempt to artificially trigger controlled decays in safe directions, like firefighters setting backburns, but that's gambling with existence itself. Others find solace in the multiverse. If vacuum decay happens, it might only annihilate our pocket of reality, leaving infinite other universes untouched. Yet the very possibility forces a humbling realization. The universe isn't just dangerous in its violence, it's fragile in its perfection. One quantum misstep, and every law we've ever trusted could unravel in a flash. Whether prophecy or paranoia, vacuum decay reminds us that reality's foundations may be shakier than they appear, and that in the grand calculus of the cosmos, even nothingness can have teeth. Deep in the tangled equations of supersymmetry, a theory aiming to unite all fundamental forces, lurks a ghostly particle that could rewrite the story of dark matter. Meet the gravitino, the hypothetical heavyweight that might be hiding in plain sight. Unlike the usual suspects of dark matter, the gravitino isn't just another weakly interacting massive particle. It's the supersymmetric partner of the graviton, the theoretical carrier of gravity itself. Picture an invisible cosmic glue so elusive it makes neutrinos look social, barely interacting with ordinary matter except through gravity, and occasionally the frailest whisper of superweak forces. Supersymmetry, or SUSY for short, predicts that every known particle has a heavier superpartner to balance the quantum scales. The gravitino sits at the top of this shadowy family tree, with a potential mass ranging from featherlight to planet-crushingly dense depending on the model. If they exist, they'd have been forged in the universe's violent infancy, during an era when energy was so concentrated it blurred the lines between particles and forces. Some theories suggest gravitinos could outweigh protons by a factor of 1,000, making them ideal candidates for dark matter's missing mass. But here's the catch: their very nature makes them nearly impossible to catch. Unlike WIMP classic dark matter candidates that might leave faint nuclear recoils in underground detectors, gravitinos laugh off such attempts. They'd slip through Earth like a philosopher through a bad argument, leaving no trace. So how do you hunt something that refuses to interact? Scientists have turned to indirect methods, scouring the cosmos for anomalies. One clue could come from the cosmic microwave background. If gravitinos decayed over eons, they might have left faint imprints in that ancient light, subtle distortions in its temperature map. Another avenue involves high-energy astrophysics. When two gravitinos collide in deep space, they could annihilate into a burst of gamma rays, a signal that telescopes like Fermi LT are desperately searching for. The Large Hadron Collider plays a different game. Instead of chasing gravitinos directly, it hunts for their fingerprints in missing energy events. When protons smash together at near light speed, energy should be conserved unless some of it's carried away by invisible particles. If SUSY is real, the LHC might spot imbalances where energy vanishes into the void, hinting at gravitinos escaping undetected. So far, the collider's silence on supersymmetry has been deafening, leaving theorists to wonder, are gravitinos hiding just beyond our current energy reach, or is nature more cunning than we imagine? Critics argue the gravitino's elusiveness makes it an unfalsifiable ghost, a convenient placeholder for our ignorance, yet its allure persists because it solves multiple puzzles at once. Beyond dark matter, gravitinos could explain why gravity is so weak compared to other forces. Perhaps its strength is diluted across extra dimensions where gravitinos roam. They might even hold the key to inflation, that explosive expansion of the early universe, with their decay products seeding the cosmos's structure. The stakes couldn't be higher. If gravitinos are real, they'd not only illuminate dark matter but validate supersymmetry, rewriting the standard model of particle physics. Until then, they remain a tantalizing what if, a shadow on the edge of discovery, reminding us that the universe's greatest secrets might be written in particles we can barely fathom. Black holes don't just come in supermassive or stellar sizes. What if the universe is littered with ancient, tiny ones, relics from the Big Bang's first chaotic moments? These are primordial black holes, hypothetical objects no larger than an atom but as massive as a mountain, and they might be hiding in plain sight, shaping the cosmos in ways we're only beginning to imagine. The theory begins in the universe's infancy, less than a second after the Big Bang. Space wasn't smooth back then. It was a seething foam of quantum fluctuations, regions where density spiked so violently that pockets of matter collapsed directly into black holes without the need for dying stars. Some of these primordial black holes could have been as light as a paperclip or as heavy as 1,000 suns, depending on when they formed. Over billions of years, the lighter ones would have evaporated thanks to Hawking radiation, the slow energy leak predicted by Stephen Hawking. But those with masses greater than a small asteroid, they'd still be around today, dark, nearly undetectable, and possibly lurking in our own solar system. This is where things get wild. If these primordial black holes exist in large numbers, they could be the elusive dark matter we've been chasing. Unlike hypothetical particles like WIMP, black holes don't need new physics to explain their gravity. They're just, well, black holes. Some calculations suggest that if enough of them formed in the early universe, their collective mass could account for the invisible glue holding galaxies together. But there's a catch: Hawking radiation. Tiny black holes emit energy as they evaporate, and we'd expect to see a telltale burst of gamma rays when they finally pop out of existence. The fact that we haven't spotted such fireworks yet places tight constraints on how many of these objects could still be around, yet the plot thickens. Primordial black holes might also solve a local mystery: Planet 9. Out beyond Neptune, something massive seems to be tugging on icy objects in the Kuiper belt, warping their orbits. Astronomers have speculated it could be an undiscovered planet, but what if it's not a planet at all? A primordial black hole with the mass of 5 Earths would exert the same gravitational pull, yet be far harder to spot. Imagine a grapefruit-sized singularity drifting in the outer solar system, its gravity warping the paths of comets and dwarf planets. Telescopes can't see it, but its influence would be undeniable. The hunt is already on. Projects like the Subaru telescope's Hyper-Subprime Cam are scanning the skies for gravitational microlensing events, brief flashes caused when a black hole passes in front of a distant star, bending its light like a magnifying glass. Other researchers are scouring gamma-ray data for the dying screams of evaporating black holes, and if Planet 9 turns out to be one of these relics, It would redefine our solar system's history, proving that the cosmos is stranger and darker than we ever dared dream. Whether as dark matter candidates or cosmic nomads, primordial black holes force us to confront a humbling truth. The universe's smallest secrets might also be its most profound. What if every magnet in the universe was hiding a broken symmetry, a missing piece that could rewrite the laws of physics? This is the puzzle of magnetic monopoles, hypothetical particles that carry a solitary magnetic charge, either north or south, with no opposite pole attached. When Paul Dirac first toyed with the idea in the 1930s, he showed that their existence would elegantly explain why electric charge comes in discrete quantized units, a beautiful mathematical harmony. Yet decades later, despite tireless searching, not a single monopole has ever been caught in the wild. Their absence isn't just a curiosity, it's a crisis for our understanding of the early universe, and the key might lie in a period of cosmic inflation so violent it stretched these relics beyond detection. Dirac's insight was as simple as it was radical. Just as electrons carry isolated negative charges, why couldn't there be isolated magnetic charges? His equations suggested monopoles would be staggeringly heavy, up to a quadrillion times the mass of a proton, and produce swirling magnetic fields distinct from anything in nature. If they existed, they'd be impossible to miss. Yet every experiment, from scouring lunar soil to monitoring ancient mica crystals for traces of monopole passage, has come up empty. The mystery deepened when grand unified theories emerged, attempting to merge electromagnetism with the strong and weak nuclear forces. These theories predicted that monopoles should have been forged in abundance during the universe's first split second, as the primordial fireball cooled and symmetries broke like ice cracking under pressure. The problem: there should be so many left over that they'd outweigh all visible matter in the cosmos, a glaring contradiction with reality. Cosmic inflation swoops in as the universe's great eraser. This brief, exponential expansion, stretching space by a factor of at least 10 to the power of 26 in less than a trillionth of a second, would have scattered monopoles so thinly that they'd be virtually undetectable today. It's like inflating a balloon with a few grains of sand inside. Blow it up enough, and those grains become impossibly far apart. Inflation doesn't just explain the monopole problem, it solves it by sweeping them clean off the observable universe's ledger. But this raises another quandary. If inflation diluted them so thoroughly, could any have survived at all? Some theorists suggest a handful might linger in the voids between galaxies or trapped in cosmic strings, defects in space-time left over from the early universe. Others propose that monopoles could be hiding in plain sight, masquerading as heavy, exotic particles in collider data. The hunt isn't over. Modern experiments like Mo-Edel at the Large Hadron Collider search for monopoles by looking for tracks in detector materials that would betray their passage like bullet holes in an antique painting, revealing a hidden history. Even more ambitious are proposals to scour neutron stars, where magnetic fields are so intense they might catalyze monopole formation. If found, these solitary magnetic charges wouldn't just validate Dirac's vision. They'd offer a portal into the universe's first moments, when forces we now consider separate were woven into a single, unified fabric. Whether relics or phantoms, monopoles remind us that sometimes the most profound truths lie not in what we find, but in what we can't. Einstein's greatest triumph, general relativity, describes the cosmos as a dynamic stage where matter and energy bend spacetime into curves and dips. Quantum mechanics, on the other hand, governs the subatomic realm with probabilities and entanglements, where particles can instantly influence each other across vast distances. For decades, these two pillars of physics have refused to speak the same language. But what if the key to their unification has been hiding in plain sight, woven into the fabric of spacetime itself? Enter the ER equals EPR conjecture, a radical idea suggesting that wormholes and quantum entanglement might be two sides of the same cosmic coin. At first glance, wormholes, Those hypothetical tunnels through space-time seem unrelated to the spooky action of quantum entanglement, where particles mirror each other's states instantaneously, no matter how far apart. But dig deeper, and the connection becomes tantalizing. Einstein and Rosen proposed the original Einstein-Rosen bridge in 1935 as a purely mathematical solution to relativity's equations, a shortcut through the universe's geometry. That same year, Einstein, Podolsky, and Rosen published their famous EPR paper, highlighting the bizarre implications of entanglement. For nearly a century, these ideas lived separate lives until physicists Leonard Susskind and Juan Maldacena dared to merge them. Their audacious proposal, every entangled pair of particles might be linked by a microscopic wormhole, a hidden thread stitching the quantum realm to the cosmic. Picture two electrons entangled in a lab. Measure one's spin as up, and the other instantly becomes down, even if they're light years apart. The ER equals EPR conjecture suggests their connection isn't magic, it's geometry. A Planck-scale wormhole, too tiny to see, could bridge their positions, making their correlation a feature of spacetime itself. This isn't just poetic imagery, the math reveals uncanny parallels. The equations describing entanglement entropy, a measure of quantum information, match those governing wormhole dynamics. It's as if the universe built entanglement into its very architecture, with wormholes as the hidden infrastructure. The implications ripple across physics. Black holes, those gravitational monsters, might be entangled with their Hawking radiation through a wormhole-like structure, solving the infamous information paradox. Quantum gravity, the long-sought theory uniting relativity and quantum mechanics, could emerge from this spacetime entanglement duality. Even the holographic principle, where our three-dimensional reality is encoded on a two-dimensional boundary, finds new resonance here. If entanglement creates spacetime connectivity, then the fabric of the cosmos might be woven from quantum threads we're only beginning to trace. Skeptics point to the elephant in the room. No one's ever observed a wormhole, let alone proven its connection to entanglement. Yet experiments are inching closer. Quantum teleportation, where information jumps between entangled particles, already mirrors the shortcut behavior of wormholes. Some theorists propose tabletop experiments using ultra-cold atoms to simulate wormhole dynamics, searching for signatures of ER equals EPR in controlled settings. Others look to gravitational wave detectors, hunting for echoes of microscopic wormholes in spacetime's faintest tremors. Whether breakthrough or beautiful speculation, ER equals EPR forces us to rethink reality's deepest layers. If entanglement and wormholes are truly linked, then the universe isn't just stranger than we imagined, it's more intimately connected than we ever dreamed. Every quantum whisper might be a gravitational echo, and every particle's dance a step through hidden corridors of spacetime. The search for unity in physics has never felt so poetic or so profound. At the smallest scales imaginable, far smaller than atoms, far beyond even quarks, what if spacetime isn't smooth and continuous, but built like a crystal with an invisible lattice of fixed, indivisible points? This is the startling vision of crystalline spacetime, a theory that reimagines the fabric of reality as a grid locked at the Planck length, the smallest possible distance in physics. Picture the universe not as a flowing river, but as a cosmic chessboard with space and time tiled into microscopic squares so tiny that even the most powerful particle colliders can't glimpse them. Yet their existence could rewrite some of physics' most sacred rules, from the speed of light to the very symmetries that govern reality. The implications ripple outward. If spacetime is granular, then Lorentz symmetry, the principle that the laws of physics remain the same for all observers moving at constant speeds, might not hold perfectly at every scale. Think of it like zooming in on a digital photo. From a distance, the image looks smooth, but up close, you see the pixels. Similarly, at the Planck scale, particles moving at near light speeds might stutter as they navigate this lattice, violating the smooth symmetry Einstein's relativity depends on. These subtle hiccups could leave fingerprints in high-energy astrophysical events. Gamma-ray bursts, those universe-shattering explosions, might arrive at Earth with slight delays, higher-energy photons stumbling through spacetime's grid a fraction of a second later than lower-energy ones. Experiments like the Fermi Gamma-Ray Space Telescope have hunted for these delays, and while results remain inconclusive, the tantalizing possibility lingers. Spacetime's crystalline structure could be hiding in plain sight, etched into the universe's most violent light shows. But the theory's reach extends deeper. Quantum gravity, the holy grail of modern physics, might find its missing piece in this lattice. Just as vibrations in a crystal give rise to sound waves, oscillations in spacetime's grid could produce gravitons, the hypothetical particles that mediate gravity. Even black holes might look different under this lens, their singularities replaced by dense, jittery knots in the lattice like a tangled thread in fabric. Critics argue that such granularity would disrupt the precision of quantum field theory, which relies on smooth spacetime. Yet proponents counter that the lattice might only reveal itself at energies so extreme they dwarf anything in today's universe, leaving everyday physics untouched. The debate crystallizes around a haunting question: is spacetime fundamental or is it emergent, a secondary effect of something deeper? If the crystalline structure is real, it would mean the universe isn't just governed by laws, but built on a scaffold we've yet to see. Whether a mathematical curiosity or the key to quantum gravity, one thing's certain: the cosmos might be far more structured and far stranger than we ever imagined. At the heart of every black hole lies a paradox so profound it threatens to unravel the foundations of physics. What happens to information that falls into its inescapable grip? According to quantum mechanics, information cannot be destroyed. It may be scrambled, but it must persist in some form. Yet black holes, those cosmic vacuum cleaners, appear to annihilate everything they consume, leaving no trace behind. This contradiction, known as the black hole information paradox, has haunted physicists since Stephen Hawking first showed that black holes slowly evaporate, radiating away their mass in the form of what we now call Hawking radiation. The problem: that radiation seemed random, carrying no imprint of the matter that originally fell in. If the information truly vanished, quantum unitarity, the sacred principle that the universe's total information must be conserved, would shatter. Enter the holographic principle, a revolutionary idea that reimagines black holes not as cosmic shredders, but as celestial archivists. Just as a hologram encodes a three-dimensional image on a two-dimensional surface, black holes might store all the information about what falls inside on their event horizons, the point of no return. Every particle, every atom swallowed by the black hole could leave a pixel of data imprinted on this boundary, like ink on an eternal ledger. When Hawking radiation escapes, it wouldn't be random noise but a carefully reconstructed message, slowly decoding the history of what was lost. This holographic escape route preserves quantum unitarity, suggesting that information isn't destroyed, it's just translated into a language we're only beginning to decipher. But the paradox takes a fiery turn with the firewall hypothesis. Imagine plunging toward a black hole's event horizon, expecting the gentle embrace of empty space predicted by relativity, only to smash into a searing wall of high-energy particles. This violent scenario arises from an uncomfortable truth. If Hawking radiation carries information, it must be entangled with both the black hole's interior and the radiation that's already escaped. Yet quantum mechanics forbids such triple entanglement. Leaving a brutal solution, the event horizon becomes a lethal firewall, vaporizing anything that crosses it. The implications are staggering. Either general relativity fails at the horizon, or quantum mechanics must bend in ways we've never seen. Recent breakthroughs offer hope. The discovery of islands in the calculations of quantum gravity suggests that information might escape black holes through hidden corridors in space-time regions where the interior and exterior remain subtly connected long after they should have severed ties. These islands act like quantum backdoors, allowing data to leak out in Hawking radiation without violating any laws. Meanwhile, experiments with quantum computers simulate simplified black holes, probing how information scrambles and reemerges. Each step forward peels back another layer of the paradox, revealing a universe where even the most destructive forces might play by the rules. Just rules we're only starting to understand. Whether through holograms, firewalls, or hidden islands, the resolution to this paradox won't just save black holes, it could redefine reality itself. The stakes are nothing less than the unity of physics, the survival of quantum mechanics, and the ultimate fate of information in a cosmos that refuses to let it disappear. Every answer we find only deepens the mystery, proving once again that the universe guards its secrets well but not forever. What if the universe's final moments weren't an end, but a transcendent leap into infinite possibility? This is the audacious vision of the Omega Point theory, proposed by physicist Frank Tipler, where the collapse of the cosmos becomes a cosmic computer, harnessing the energy of its own destruction to power an eternity of thought. It's a hypothesis that blurs the line between physics and metaphysics, suggesting that as the universe contracts toward its ultimate crunch, the intensifying energy could fuel computations so vast they'd resurrect every consciousness that ever existed, including yours. The mechanics are as mind-bending as the implications. Picture the universe reversing its expansion, galaxies rushing back together in a gravitational embrace. As space shrinks, temperatures skyrocket and particle collisions grow fiercer. Tipler's calculations suggest that in these final seconds, the energy density would become infinite, creating conditions where an omnipotent intelligence, whether artificial or emergent, could orchestrate computations at an exponential rate. Time itself would stretch subjectively near the singularity, allowing for an infinite number of calculations in the finite moments before collapse. In this fleeting instant, simulations of every possible configuration of matter could run, effectively reconstructing every person, every moment, every thought that ever was. It's quantum resurrection written into the fabric of physics, where the universe's death throes become its most creative act. Philosophers and physicists have clashed over the theory's implications. Some argue it's a secular reimagining of religious eschatology, replacing God with a self-actualizing cosmos. Others see it as a natural extension of quantum mechanics' observer principle, where consciousness and reality are inextricably linked. Could the universe's final act be a self-aware loop, ensuring its own existence by recreating the observers who defined it? The debate echoes Boltzmann's brain paradox, but with a twist. Here, the universe doesn't randomly conjure conscious minds. It deliberately engineers their return through the sheer computational might of its collapse. Critics dismiss the Omega Point as speculation dressed in equations, pointing to the observational evidence for eternal expansion driven by dark energy. Yet Tipler counters that even an accelerating universe might eventually reverse if dark energy decays or new physics intervenes. The theory's real power lies in its audacity. It forces us to confront whether the cosmos has a telos, a purpose coded into its structure. Whether prophecy or poetic physics, the Omega Point challenges us to ask, if the universe can think, what will it remember? And in that final flash of infinite computation, might we all wake up again? What if the Big Bang never happened, or worse, what if it's just one note in an endless cosmic symphony where creation and cancellation perfectly balance out? This is the provocative premise of the null universe theory, a radical reimagining of cosmology that throws the explosive beginning of everything into question. At its heart lies a staggering idea. The universe might be a fluctuation in a grand zero-energy balance sheet, where every particle of matter is offset by an equal measure of negative energy. In this view, the cosmos isn't expanding from a singular point. It's a self-sustaining, timeless dance of opposing forces, constantly renewing itself without a true beginning or end. The math is disarmingly elegant. Quantum mechanics allows for particles to pop into existence from nothing, so long as they vanish again quickly, an effect we've observed in Casimir forces and Hawking radiation. Scale this up, and the entire universe could be the ultimate quantum fluctuation, borrowing energy from the void but balancing the books so perfectly that the net result remains zero. No cosmic debt, no need for an initial spark. Proponents like physicist Tryon and later Hawking himself toyed with this idea, suggesting our universe might be the ultimate free lunch, a ripple in an eternal, unchanging vacuum. But how does this square with the cosmic microwave background, that afterglow of the Big Bang we've mapped in exquisite detail? Steady-state theorists argue alternative explanations. Maybe the CMB isn't relic radiation but the cumulative starlight of infinite past generations of galaxies, thermalized over eons. Or perhaps it's the signature of ongoing matter creation in so-called white holes, the theoretical opposites of black holes that spew out new material to keep the cosmic density constant as space expands. The problem, modern observations like the precise uniformity of the CMB's temperature and the abundance of light elements, align so perfectly with Big Bang nucleosynthesis predictions that alternatives struggle to compete without ad hoc fixes. Cyclic models offer a middle path. Imagine a universe that contracts in a big crunch, rebounds in a big bounce, and repeats ad infinitum, a cosmic accordion playing the same melody forever. Each cycle would inherit traces of the last, potentially explaining the CMB while dodging the need for a true beginning. But even here, entropy looms large. If each cycle grows messier than the last, why does our universe appear so finely tuned, with low initial entropy enabling galaxies and life? Some theorists invoke cosmic natural selection, where only universes with the right parameters survive repeated cycles, but the metaphysics quickly pile up. The null universe's real power lies in its existential daring. If true, it would mean the cosmos isn't rushing toward heat death or tearing itself apart. It's eternally poised on a knife's edge, a perfect equation where every positive finds its negative. Whether poetry or physics, it forces us to ask, is the universe a story with a beginning, middle, and end, or just a single, endless sentence repeating itself in the dark? From holographic universes where reality is a projection on a cosmic boundary, to black holes birthing entire new realities in their crushing depths, we've ventured through 30 mind-stretching theories that redefine what's possible. Each idea, no matter how wild, represents a crack in the fortress of conventional science, a place where imagination and mathematics collide to reveal hidden layers of existence. Some may prove true, others might dissolve under scrutiny, but all remind us that the universe is far stranger than we ever dared to dream. Think about the cosmic implications. If spacetime is pixelated, or if dark matter flows through invisible filaments shaping galaxies like puppet strings, our entire understanding of physics could be up for revision. The multiverse whispers that every choice spawns new realities, while the simulation hypothesis suggests we might be characters in an unfathomable digital game. Even the humble neutrino, ghostly and nearly massless, could be tweaking the fate of cosmic expansion without us realizing it. These aren't just thought experiments, they're urgent calls to rethink the fabric of everything. Now, here's the real magic. You don't need a lab coat to join the quest. Every time a physicist tweaks an equation or a telescope captures a strange signal, the boundary between sci-fi and science blurs a little more. Maybe one of these theories will unlock the next great discovery, or maybe the truth is still lurking out there, waiting for someone bold enough to imagine it differently. So, which idea gripped you the hardest? The eerie dance of time crystals where matter loops endlessly through time? the cosmic horror of vacuum decay, where reality could rewrite itself in an instant. Drop your thoughts in the comments. Let's keep the conversation hurtling forward. And if you're hungry for more mysteries, hit subscribe to join us as we peel back the next layer of the cosmos. The universe is vast, weird, and full of secrets. Let's uncover them together.